Welcome, ladies and gentlemen, and thank you for joining me on my presentation for my P2 practical report. Now, this is the automation of the UV Catalytic system, and this is brought to you by Rainwater together with UNISA. So, what I will be speaking to you about is the abstract, the introduction, the aim, the literature review, methodology results, and conclusion of this system.
So in this presentation, we'll be examining the design and the automation of a water purification system that utilizes UV and titanium dioxide in order to treat contaminated water. Now, this is a proposed system that is both innovative and efficient in approaching the treatment of contaminated water. We are simply just trying to develop sustainable and effective water treatment systems that can meet the growing demand for safe and clean water.
So in this presentation, we're just simply examining the design as well as the automation of a water purification system that utilizes UV together with titanium oxide in order to treat the organic material, the algae, the nitrogen, the bacteria, the viruses that are present in contaminated water. So we're just simply talking about advanced technology of combining the properties of a catalytic chemicals such as that of titanium dioxide together with UV radiation in order to form a bond that will eliminate the possibilities of illnesses and bacteria and viruses that live in contaminated water so that the output could be clean water. Unfortunately, South Africa is facing a crisis of contaminated rivers and dams, which most cases this is where people who reside in tribes and in rural areas and so forth go in order for them to get water for daily use. So now this water that they're using now is filled with toxicants. It's filled with blue-green algae. So such water needs to be treated so that they can be able to use it without threatening their health. So a solution needs to be derived, or rather, we need to develop a solution that will help them clean contaminated water so that at the end of the day, they do not expose themselves to the risks of ill health. The research work is aimed at developing a highly efficient and cost-effective water purification system with the utilization of UV and titanium oxide. Now, this has to be a low-cost, automated water treatment system that is capable of killing the bacteria and viruses or removing bacteria and viruses that is in water, so that such water can be able to be used for human consumption. So our literature review speaks to the different concepts that could have been applied or that are available for solving such a problem. These are previous authors who have went through the process of researching and coming up with ideas that can solve this problem. So we looked at four concepts, or rather four methods that could be applied in solving this problem. The first concept is that of chlorination. This is just simply the process of adding chlorine into drinking water in order to kill viruses, parasites, and bacteria. The second is ozonation. Ozonation is just the process of the creation of ozone in an ozone generator, which is then injected into water and immediately starts to oxidize and eliminate contaminants in water. Then we've got the third concept, that is just simply the use of UV irradiation. The system, or rather the water in the system, is exposed to UV light, which is then used to kill the bacteria and the viruses in water. And then we've got the fourth concept, which is the combination of UV radiation as well as titanium dioxide. In this process, the titanium dioxide is exposed to water, which then generates reactive oxygen species, ROS, that can break down organic compounds into simpler and less harmful substances. So this part of the presentation speaks to the methodology. And here I will be explaining how the operational cycle operates, and we also have our flow diagram. This is just simply talking about the main components that make up our system. So here we have our computer. This is where we code our system, rather write the code for our system. Then we load that into the microcontroller. By pressing just the start button, we are communicating with the pump to fill the system. The ultrasonic sensor is communicating with the microcontroller to say the system has been filled to the level that is required. Stop filling the system. The vessels are filled. The TDS sensor waits for the water to be treated by the combination of the doping chemical together with the UV light. And once that process is done, the TDS sensor awaits the water to be removed out of the vessel so that it can test the TDS levels. Now we are saying pump 2 pumps out the water out of the 3 vessels so that the TDS sensor can be able to detect the TDS levels of that water. If it's clean water, we've got water coming out of the system into our clean water vessel ready for human consumption or use. If it is not, we have recirculation and the process starts all over again. In this part of the presentation, we're looking at the results. This is how the final prototype looks like, as well as how the system operates in terms of filling the system with water, passing it through the doping, as well as the UV vessels, and all the way through to the filtration vessels. So please look at the following video as it illustrates and explains the operation of the system. This is where we have our doping chemicals in here. So we start here with our contaminated water. Our contaminated water is passed through this doping chemical which is in this bucket. From there it flows into these 3 vessels. As you can see here we have our UV lights, and then out of there we have our TDS sensor. This tells us if the TDS level of the water, if it's safe for human consumption. If it is, as illustrated, said, it goes into this bucket or vessel where we filter the water. This is our filtration system, and we filter out the chemical, and then it goes here, which then stipulates that our water is clean and ready for human use or for human consumption. So I will start the system, and let's see what happens. We press our button. It starts our pump to pull water into the system. We switch on our lights, right? Because for the illustration, this is clean water. What happens is our TDS sensor has already stipulated that the water is clean for human consumption. And if you can just come close. So if you can see, just shine into this bucket. If you can see, the water is coming into this filtration vessel because the TDS sensor has indicated that the water is safe for human consumption. If it was not safe, water would not enter here, but instead it will go back into the system for recirculation, so it goes through the same cycle. So what we have here is our prototype together with our poster, which was utilized during Innovation Day for our presentation to illustrate how our system operates when it is treating contaminated water. So looking at our two graphs, these are graphical representations of the tests performed by our system when it was testing the contaminated water TDS levels as well as testing the clean water TDS levels. So TDS levels are the ones that tell us whether or not the water is safe to be taken out of the system and used or consumed by humans. Looking at the table at the top right, it shows us the different levels of TDS and whether or not they are good or bad for consumption. So the graph on the left is showing high levels of TDS. Looking at it, it is showing levels between 1,184 to 1,174. Now, our table tells us that anything between 900 and 1,200 is poor. Poor is not good for human consumption. So, therefore, such water, according to our system, will not be exited out of the system. Instead, it will be taken back into the recirculation until the water reaches a TDS level that is acceptable and therefore can be used by humans. But looking at the graphical representation on the right, it shows the readings of clean water. This is ranging from 107 to 102 or 102 to 107. So that TDS level, looking at the table, says that anything less than 300 is excellent. So the TDS reading here is showing a value that is less than 300, showing that that water is excellent and good for human consumption. So these results are showing that our system, it is more than capable of testing and producing results in order for you to know the type of water that has entered the system and if the water is ready to be exited out of the system and be used. So in conclusion, we can say that our water purification system is excellent for A, detecting the state of water, or rather the TDS levels of water, and B, determining whether or not such water should remain in the system or be taken out of the system because it is not deemed good for human consumption, or C, rather together with C, clean, circulate and clean contaminated water until it reaches a TDS level that is deemed good for human consumption. So here we have built a prototype that uses the state-of-the-art sensors that are able to test and determine the purity or the cleanliness of water and inform you by means of an LCD screen as the consumer or the user of the system the levels that the TDS sensor is sensing. So you are also part of the progress or rather the system as everything else is happening. You are able to stay informed and know how far is the cleaning process, at what level is the TDS water that is being tested, and if the water is clean or not clean for human consumption. So such a system is a good and reliable system and can be trusted to tell us the state of the water and also give us water that is good for human consumption. This is the end of the presentation. Thank you so much for taking your time and listening to my presentation. I hope that I have shared enough to encourage you to find even better systems of purifying and maintaining clean water.